A very good morning to all of you. I'm Amit Jain, Senior Energy Specialist from the World Bank, and I will be the moderator for today's session. I welcome esteemed speakers and the audience to this session. Very quickly, about myself, I have been with the bank for 7 years now, and I'm part of the Energy Storage Partnership. As a background, I have a PhD in solar, and I have been working in the area of renewable energy for the past 20 years now. Before I hand it over to my esteemed panelists, I would like to give a very brief context why we are here today. 15 to 20 years back, there was a discussion how expensive solar and wind are. Today, that discussion has moved from transition from renewables to global net zero. Again, 15 to 20 years back, when we were talking about pilot projects on solar home systems, on solar parks of the scale of 50 to 100 megawatts, today we are talking about 100% clean energy. There is a clear energy transition shift talking about global net zero. As the electric grid starts depending more on the intermittent solar and wind power rather than the fossil fuels, utilities that just a couple of years ago were looking for batteries to store 2 to 4 hours of electricity are now asking for systems that can deliver 8 hours or more. It is then when we talk about long duration energy storage technologies, and that's the reason we are here today. We all know when the penetration of renewable energy increases more than 30%, it may have a destabilizing impact on the grid. The role of storage becomes very important, and the role of long duration energy storage becomes all the more important again when we talk about net zero and we talk about higher penetrations of solar and wind. There are several studies which indicate that an electric grid that is 80% powered by solar and wind would require at least 12 hours of storage energy. Currently, about 90% of the long duration energy storage in the United States is from pumped hydro. However, due to limitations by geography, pumped hydro cannot be applied everywhere. And that's the reason there are new upcoming technologies which we will hear from our esteemed speakers about long duration energy storage. The push to decarbonize the electricity sector and to stabilize the climate, the role of long duration energy storage is becoming all the more important as we go forward towards increasing penetrations of renewables. With this, I would like to introduce the speakers. First, Mr. Adam. Mr. Adam's career has spanned over 3 decades, advancing new battery and fuel cell products for energy storage, consumer electrics, military and industrial markets. Adam has led Duracell's OEM sales and consulting group. He was the president of Millennium Cell and CEO of Econometrics, fuel cell technology developers and manufacturers. Most recently, as a chief commercial officer of NEC Energy Solutions, he led the capture of grid-scale energy storage projects for leading energy storage integrator over a 4-year growth period. As you can see, Adam is the right expert which we need today to advance the long duration energy storage. Just housekeeping, we have allotted about 25 minutes for Adams for the presentation. Then we will take up questions which will be for 15 minutes, and then we will move on to Adam. Adam, over to you. We are all very excited about your presentation.
Thank you, Amit. While I share my screen, I'll say welcome everyone. I'm coming to you from Boston, Massachusetts, where it's a little after 8 a.m. And I'm happy to be talking to people around the world. Amit, can you confirm that you can see my screen? Great, thank you. So Ambry is a new battery technology company that was where the technologies were invented at Massachusetts Institute of Technology and spun out into Ambry, which is named after the center of Cambridge, which is where MIT is based. So we have a brand new battery technology and look forward to talking to you about it. So it's designed for long duration energy storage, so 4-hour to 24-hour duration applications. And this battery technology is particularly designed for daily use, meaning most applications are going to be shifting energy from the period of the day when renewable generation is at its peak, typically middle of the day, to the period of the 24-hour day when the demand for electricity is at its peak. In most places, that's between 4 p.m. and 10 p.m. So it's that daily cycling back and forth, which is this battery system is designed to achieve. And of course, right now, the battery industry for energy storage is dominated by lithium ion. So we have tried to portray this technology relative to lithium ion so you could understand the trade-offs there. So first of all, Ambry's system has a CapEx at 25 to 50% below a 4-hour lithium ion system. And we can beat lithium ion pricing there, then we can more easily beat it at 6 hours, 8 hours, 12 hours. Part of the reason the economics are so attractive is because it does not have any meaningful degradation. It has a 20-year lifetime with a maximum 5% degradation over those 20 years with an everyday usage during those 20 years. So that translates into 7,300 cycles. The battery system does not exhibit any degradation in capacity due to usage. So it could be 2 cycles per day, 3 cycles per day, not really a problem. It's a very strong safety aspect to this technology. So it does not have a thermal runaway mechanism. And that's because the technology does not generate gas inside the cell under any circumstances. Typical circumstances where other batteries will generate gas is when they're short-circuited or overcharged or over-discharged. So this battery chemistry doesn't generate gas under those circumstances, so it does not increase pressure and then increase temperature and pressure and temperature until ultimately other battery chemistries need to vent off either hydrogen or organic solvent like lithium ion. So it avoids the most typical safety risks associated with lithium ion batteries. And then these batteries are made out of calcium and antimony. So it is not a battery materials that are used in other batteries or EVs particularly. So it does avoid the difficult supply chain issues that lithium ion is suffering today. So you can see in the lower right corner that this battery system will be delivered in a containerized form, similar to lithium ion batteries are done for the energy storage market today. And they are paired together with typical inverters, transformers, in order to provide power to the grid wherever they happen to be located. Uniquely, these battery containers can be stacked on top of each other in order to minimize the amount of land that's required for an energy storage system. So Ambry will be building factories to produce the cells, produce the containers, and we'll be delivering them directly to utilities, IPPs, and developers in the grid scale energy storage market. And we will be building those manufacturing facilities first in the United States and then later in other international locations. And Ambry's investors are led by Bill Gates, Reliance out of India, Paulson and Company, and other investors out of New York and Japan. So this is what the product looks like. It is a cell-based technology, similar to other batteries, has no moving parts among the cell, or as we package those cells into what we call trays, and then we place those trays in a stack inside the container. Again, no moving parts throughout. Therefore, you have a battery system that once it is commissioned, then there is no need for preventative maintenance or scheduled maintenance. It is designed to start operating for daily cycling and will have a 20-year life without maintenance. A couple other features associated with this container. So it would be a 1 megawatt hour container with a maximum power of 250 kilowatts, which would be your 4-hour discharge. Of course, you can operate at 125 kilowatts, which would be an 8-hour, and so on to up to 24 hours. It is a high temperature battery system, and that's what makes the ability to use these unique materials. So at the production of these cells and the assembly of this system, shipping and installation of the system, all of the parts and the cells are at room temperature. And at room temperature, the calcium and the antimony and the electrolyte, which is primarily calcium chloride, are essentially inert. There is no voltage across the cells at room temperature. So there is no risk of a short circuit or a arc flash or any of those issues that are typical among large battery types of assemblies. So we ship those containers directly to project sites, and then we will place them onto foundations or pads, hook them up to external connections, and then ready for commissioning means we connect to a source of electricity, which we use in order to operate heaters, which are inside the container. The heaters warm the interior of that container. And as you can see on this, there is a layer of thermal insulation inside the container, on the inner walls of the container, and that retains the heat inside the container. So after heating to its operating temperature, then we can disconnect from those heaters and start charging and discharging this battery. And just like the battery in your cell phone, if you use it, then it gets warm. So we trap that heat inside the container that keeps it at its operating temperature without any need for auxiliary power in order to provide heating. And of course, because we want this battery to operate at its operating temperature, we have no cooling HVAC or other ductwork either. So that's part of the reason you can stack these containers on top of each other. They are just cubes of energy storage, and otherwise they're just like a typical battery system. They have instantaneous response, which is very important for operating, whether it's primary reserve or frequency regulation or other short duration types of applications, while at the same time they could be shifting blocks of energy from some hours of the day to another hours period during the 24-hour day. You can charge it at up to 4 hours or slowly into 24 hours, and you can discharge it fast at 4 hours or slowly at 24 hours. So it's quite a versatile battery system once it's installed and commissioned. And this is Ambry's roadmap for bringing this technology to market. So we are in the process of commissioning our first system. This is the 40 kilowatt hour system, which is a pilot system for a data center. And I'll show you what that looks like. So this is the actual tray that I was just showing you a graphic of. And so inside this tray are 22 cells and an electronics interface. We take those trays, we load them into the container. You can see that this container has 12 trays loaded into it with the electronics interface on the exposed side here. And then we have a BMS, a battery management system, for each stack of these trays, all inside, in this case, a 20-foot shipping container. And this battery system is intended to be used for evaluation of the technology. It is hooked up to a UPS system and a server rack from a data center, in order to demonstrate that it can power those objects, that it can be used for immediate power in the case of a grid outage. And it also will be used in order to demonstrate that it can shift energy in a renewable environment. It can perform frequency regulation and various other real world tests associated with this battery system. And then once we go through those tests, it will be put on a daily cycling regime for over a year in order to demonstrate that it didn't suffer any performance loss by doing all of those different types of tests, and that it demonstrates no degradation over that 1 year of usage. And next year, we will be producing a higher energy density system. So we're going from 40 kilowatt hours to 300 kilowatt hours in a 10-foot container system, and then 690 kilowatt hours, and then 920, and then 1 megawatt hour inside those containers. You can see that each one of these containers will be certified by Underwriters Laboratories to UL 9540, 9540A. And then Ambry is currently producing at our facility outside of Boston, Massachusetts. We have recently signed access to a 140,000 square feet, or about 14,000 square meter facility, also here in Massachusetts, in order to build our prototype systems that are coming next year. And then we'll be building a large-scale, high-volume manufacturing plant in the United States, which will open in mid-2024, and we'll have a capacity of 3.1 gigawatt hours in 2025, about 5 gigawatt hours in 26, ultimately about 14 gigawatt hours at the end of the decade. So that's Ambry's roadmap and how we're coming to market. So the important things to keep in mind are our first commercial systems will be shipped in 2024, about 200 megawatt hours of those. And I'll show you the type of system that we expect those to be. But first, I want to talk about the technology just a little bit more. So calcium and antimony are unusual materials for a battery system. As far as we know, Ambry is the first company to work on those electrode pairs. And as I said, the company was formed in 2010, so we've been working on this technology for quite a long time. We've chosen this combination because of its cost profile primarily. You can see here the electrodes for an Ambry battery cost about a third that of a lithium NMC battery system. So inherently, we just have a lower cost set of materials. And those, as I said earlier, are enabled by the fact that we operate at a high temperature. So the calcium melts into a liquid at its operating temperature, and the electrolyte, which is primarily calcium chloride, also melts into a liquid. And that's why we call this a liquid metal battery. And the fact that those two components are liquids is what causes the battery to have a very minimal type of degradation profile across its 20-year life. So primarily degradation in batteries results from mechanical issues. So either they are substrates, which either stress under mechanical charging and discharging, and they trap ions, which therefore are no longer available for charging and discharging, and the battery slowly loses energy as a result of that, as well as interface layers between the solid electrodes on both the anode and the cathode side. So the Ambry system avoids those mechanisms of degradation because of the liquid nature of its anode and its electrolyte. And the way the chemistry works is you can see in a charged state, essentially you have calcium and antimony separated by an electrolyte. And as you discharge the battery, the calcium gives off 2 electrons, and calcium 2 plus ions flow across the electrolyte to form an alloy with the antimony at the cathode area. So this battery system can be driven completely through to its complete reaction. So therefore, all of the calcium can be utilized. And then upon charging, the calcium 2 plus goes back across the electrolyte, forms elemental metal calcium on the anode collector, and again can be driven all the way to the full calcium is back in its spot on the negative current collector. So it means that a battery can go from 0% to 100% to 0% without any concern for the health of the battery or any safety related issues. As many people know, most other battery systems typically only go from 5% to 95% in order to avoid issues at the very top and the bottom of the state of charge. Now you can see here a depiction of the cell, which is the core of the technology. And in this case, this is the cell that we've been producing for the last 20 months. It is a 3 conductor on the anode side plated cell. So we have you can see in this actual picture down here, the positive or the cathode fits inside these narrow slots here. And then in between those slots, we essentially have plates, which are the negative current collector that fit in between those. And then in that case, you can see you have 4 bays where you have cathode material and 3 places where you have negative anode material, all in parallel, so making a single cell. This is a hermetically sealed cell that's about the same size as the battery that starts your car. So a lead acid battery that starts your car, that's essentially what you ought to be picturing. The rest of the materials are all stainless steel. So that's what you're seeing here is the picture of the cell on the outside, which is all stainless steel, and all the other components in here are stainless steel as well. So it's a fairly simple battery to manufacture. Essentially, it is 2 powders, which are the anode and the cathode, and then the liquid electrolyte, which we melt and pour in as a liquid. And then you weld shut the cell, and it makes for a fairly simple and reliable cell. And so here's some performance data associated with how these cells perform. Again, this is across, so C/4 means that you're operating at a power to result in a 4-hour charge or a 4-hour discharge. So C/10 means 10 hours, C/20 means 20 hours. You see the efficiency ranges from 94% to 86% across that power range. Here are the shapes of the voltage curve. You can see this goes from about 1.2 volts down to about 0.6 volts at the bottom of discharging. And otherwise, very similar to other battery systems, as you probably have seen. And again, been making these particular cells for about 20 months. You can see here some cycle data. One of the unusual things about these cells is that their capacity typically increases over the first 1,000 cycles, and then it flattens out for the remainder of its life. The same is true for efficiency, typically rises and then flattens out for the rest of its life. So we forecast no degradation in efficiency or capacity over those 20 years, although we do provide a guaranteed warranty of no more than 5% degradation over that period. And then quickly about the end of life of these batteries. So kind of an interesting thing, if you stop using this battery, then it will cool down. And at the end of life, that's what you do, essentially just stop using it. And when it has reached its room temperature, then we can take the cells out, they are now again full of solid materials. If you cut them in half and place them in a bath of water, then the calcium and the calcium chloride will dissolve into the water. The antimony and the stainless steel will not. So they are easily separated out. There is an active recycling market for antimony and stainless steel today. So about 30% of the antimony usage today is recycled antimony. So it is easy to recycle these batteries. It's about a $35,000 value to these materials at the end of life. So there's a positive value to the battery system when you decommission it 20 or more years down the road. And I've mentioned that these batteries are quite safe. So this is the testing recently successfully completed with Underwriters Laboratory at the cell level. So UL 1973 is the typical but difficult safety certification for rechargeable batteries. And lithium-ion batteries, for example, will pass this test, but only if they are in a module which has safety electronics around those cells. Essentially, if you short circuit a lithium module, then a switch will open up, stopping the current through that cell. And that's perfectly fine. It makes for a safe lithium-ion module, and that's how they pass those types of tests. In Ambry's case, we do not use or require any electronics around the cell. None were used in this certification. So they take it through the same type of tests. They raise it to an elevated temperature. Then they raise the cell to an elevated voltage, which is essentially overcharging. And then they will short circuit the cell. And under all cases, the pass and fail is whether there's a fire or explosion. And in Ambry's case, none of those things occurred. Not only that, but we put the battery back on performance testing after going through all of those abuse tests, and the battery showed no signs of being degraded as a result of those types of abuse tests. So not only very safe system, but very robust, right down to the core cell level, which means that this battery system will easily pass all the UL 9540 and 40A type testing. We've also put it through transportation testing. Of course, as I said, when you transport these cells, they are at room temperature. That means it's solid metal inside, essentially inert. So you can do basically anything to them, and the typical testing under UN 38.3 involves shock and vibration and elevated temperature, short circuiting, crushing, various other things, none of which cause any problems for the Ambry cell. And so when we bid on projects, we will typically bid in this type of a structure. This happens to be a 4-hour discharge system, so 32 megawatt hours with a power capability of 8 megawatts, so 4 hours of operating time. We marry, in this case, 32 1 megawatt hour containers with 8 megawatts of inverters and a 9 MVA or 9 megawatt transformer. So that could be a standalone project. And this is the size of the projects that we're doing in 2024. But in addition, this can be a building block for a larger project. So that same system I just showed you, we would use 38 of those laid out across, in this case, a little under 5 acres of space, or about 2 hectares of space, in which you'd get a 300 megawatt, 1.2 gigawatt hour energy storage system, which is about the same as the best lithium ion in terms of land usage. So in the case of large solar storage systems, we could move from lithium ion to Ambry without any sacrificing any land. And then Ambry's plan going forward is to, after we have built our US manufacturing facility, we will be moving on to building exact replica facilities outside the United States. So we are currently talking to parties who want to build in Europe, in the Middle East, and in Asia. And so our plan is to have those 4 manufacturing facilities come online one at a time. And so that by 2030, we have a total manufacturing capacity of about 50 gigawatt hours. And each of those manufacturing facilities, of course, would deliver primarily to the regions in which they operate, but could deliver to wherever they wanted to if they had a customer. So I think that's the end of my presentation. So I appreciate everybody's time, and I look forward to any questions that anyone has.
Thank you very much, Adam. I myself has a lot of questions for you, but let me first start from the questions from the audience. I will take 2 questions, Adam, at a time so that we are able to cover all the questions. The question from Brendan is, do you have any UK partners who are using Ambry? The second question on the pricing from Jan and Sally is, what will be the cost per kilowatt hour? And a related question, storage price of Ambry. Let me first stop here. Over to you, Adam.
Okay. So the first question regarding partners in the UK. So right now, the UK is, I'm not aware of many projects in the UK which are in the 4 to 24 hour duration range. UK has had a lot of successful lithium-ion projects which have been deployed, and they range from about 30 minutes to about 2 hours in duration. There's some discussions about some longer duration projects there, and we have had some with some of the developers there, but they still seem to be a little ways off. And the issue there, of course, is that there isn't an economic reason to have long duration. And so that market needs to develop before there's a significant amount of long duration demand, in our opinion. Regarding pricing of Ambry systems, so we're talking about this container here, so 1 megawatt hour container in a 10-foot container. We're pricing that between $160 and $180 per kilowatt hour, depending on the year of the project and the size of the project. So if the project were, for example, on the size scale of this 1.2 gigawatt hour project, which happens to be a project that Ambry has been awarded in South Africa, then we would be at the lower range of that pricing, because we would be delivering that starting in 24, but through 2026, because as you can see in the graphic here, there are 4 tranches associated with this project. Whereas if we were delivering a project that was approximately this size, then we would be in the higher range of that pricing.
Thank you. Adam, shall I move on?
Please do.
Okay, we have now 3 questions on temperature and long duration batteries. And I have also this question, Adam. Now, I'm from a tropical country like India, where currently the temperature is 50 degrees centigrade. And there have been several instances of fire in the battery systems. So we have 3 questions for you. How sensitive the battery performance to temperature and temperature fluctuation? What is the ideal temperature for efficient functioning of the battery? And when the load is very low, how does it keep working temperature without the heater? Over to you.
Yeah. Okay. So the design of this container, as I mentioned, it has thermal insulation inside the walls. It serves 2 functions, right? One is it keeps the high temperature in. It also insulates the inside of the box from whatever the temperature is on the outside. So honestly, you can see here an external temperature range specification is quite broad. There is no dependency or any impact on the performance of this battery from whatever the ambient temperature, whatever the outdoor temperature happens to be. So again, it could be 50 degrees C or higher. There's no need for cooling for this battery system. And therefore, for the same reason, it could be minus 50 degrees C outside. Doesn't matter to this battery system. It maintains its temperature on the inside of the container to it during it or within its operating range, you can see here. That does make it quite a suitable battery for temperature extreme locations. And again, by no dependency, I mean the efficiency doesn't change, the capacity of the battery doesn't change. It's really no impact whatsoever from outdoor temperature. Let's see, what was the other question? About low usage, yeah. So the battery system is designed to maintain its operating temperature down to, with no assistance from any electrical power for heating, down to about 0.5 cycles per day. So this battery is designed for applications where reasonably predictably you're going to do a full charge and discharge every day. And that is typical with a solar plus storage or the typical type of renewable integration battery plus renewable project. Of course, it is possible that the usage could stop. And if you stop using altogether, you have some choices. One of them would be to just let it cool down. And it would take 10 to 14 days for the system to actually cool all the way to room temperature. Of course, you have other options, which would be to use some electricity in order to maintain the interior of the container at its operating temperature. So at about 3.5 kilowatts of power per 1 megawatt hour container, it would maintain its operating temperature and always be ready for charging and discharging. Of course, the most economical option there would be to use the battery. And because it's a battery system that doesn't suffer degradation due to usage, then even the most unattractive, maybe that's not the best way to put it, even a relatively low revenue or value usage of the system is still an opportunity to either make money or save money, depending on the usage case of the particular battery system. So we would encourage people to arbitrage electricity prices from the low period of the 24-hour day to the high price period in the 24-hour day as a way to always be able to make money and to use the battery, which would keep it at its operating temperature through usage. So there's a lot of different options available if daily usage is not likely to be the case.
Thank you, Adam. Adam, we have tons of other questions. I'm going to take the last set of questions for you, but I think you may have access to the chat box. So once this is over, if you have time, you may respond to some of the questions which we are not able to take online. So question from Surbhi is, what are the typical use cases for long duration batteries that are required for commercial viability? From Aditya, what is the residual value of battery, which is metal recycling as a percentage of capex? And finally, from Andrew, what are the capacity degradation mechanisms of this technology? And do these cells exhibit calendar and cycling aging phenomena? Over to you.
Okay. You're testing my ability to remember all those questions when you ask them that way. Okay, so I'm going to go backwards. Let's see. So all batteries have a certain calendar life to them. It's just the nature of the law of physics is escaping me. That nature doesn't allow organized matter to stay in an organized fashion forever. So ultimately, you're going to see a breakdown in every battery system on a calendar basis. That's part of the nature of our 20-year lifetime claim on this battery system, is that we are confident that you will not see meaningful calendar degradation over a 20-year period. But sometime after 20 years, you'll start seeing maybe some corrosion from the outside in, or maybe from the inside out. We have obviously measured that. It's an incredibly slow acting process, but eventually, that will take over. And let's see, the value at the end of life, as I've already indicated, it's about $35,000 for the value of the antimony and the stainless steel within the cells that are part of this containerized system. Of course, there's also value to the container, maybe some value to electronics. And so that compares to about between 150,000 and 180,000 CapEx for that battery system. So those are the numbers behind that question. And I think you had one more question. I've forgotten what it was, Amit. Can you remind me?
What are the typical use cases for long duration batteries that are required for commercial viability?
Right. Yeah. So the interesting thing is that there's quite a number. And it's important, particularly in various countries where there is not a lot of energy storage today, and there is anticipated to be a process of decommissioning greenhouse gas producing power systems. Those greenhouse gas systems are keeping the grid stable, not only because they provide a steady base load of power, but they all participate in certain ancillary service markets like primary reserve or spinning reserve or various other things like that, which require the power system to be able to ramp up and ramp down in a relatively short period, in a relatively short response time. So, there are a lot of energy storage technologies out there. We're gonna hear from a flow battery manufacturer next. There are gravity-based systems like pumped hydro. There's compressed air. There are thermal systems where you're heating up rocks and various other things. So, part of the reason that batteries have been successful in energy storage is because they're like a Swiss Army knife. They can be used for very rapid response, or they can move energy slowly across a longer period of time. So batteries are good at that. This battery system can do that as well. It can go from zero power to full power in less than 1 second. And that's what lithium-ion batteries are doing, for example, in the UK to perform against the balancing mechanism or the EFR market, which are all kind of quick response. But typically long duration systems are going to be put in place primarily to shift energy. And that energy shifting could be, as I said earlier, an arbitrage between the low price of electricity during the middle of the day when solar is at its peak generation. There are many places around the world where the price of electricity goes negative on the wholesale market. So that's a good time to charge a battery. And then later in the day, or maybe in California, for example, the peak time between 4 p.m. and 10 p.m., where the price of electricity is in the between 5 and 20 cents per kilowatt hour. So shifting energy between those two price periods, we call that arbitrage, is probably going to be the most popular use for long duration energy storage, because it basically helps cover the 24-hour day from renewable energy. The other popular cases are going to be at the corporation level. So there's a number of, or maybe almost all large corporations are thinking about how to achieve not just net zero, but 24/7 renewable power. And in order to do that, they need long duration systems in order to shape their load curve so that it matches the generation curve of renewable, be that wind or solar or hydro, whatever renewable resource they're looking for, you need batteries in order to essentially make those curves align. And there'll be quite a lot of demand for energy storage systems in order to create that shaping. So I'll leave it at that.
Okay, thank you very much, Adams, for these useful insights. Unfortunately, we don't have much time to answer all the other questions, but there are at least 20 more questions for you, which will probably require another hour for us to brainstorm with you. Thank you very much, Adam. And we will now move on to the second leg of our presentation. I would like to introduce Mr. Adam. He's into international government relations and project management, and he covers various donor-funded and private sector initiatives in several countries in South Asia, in Asia, and also in Lebanon, Kenya, and several parts of Africa. His principal focus have been leading business development and government affairs efforts in energy and infrastructure security, specifically into energy trade, energy sector liberalization. So Aaron has tons of experience into long duration energy storage as well. With this, Aaron, I will hand it over to you. As I mentioned, you have approximately 30 minutes for presentation, and then we will take questions now.
Well, thank you very much, and it's a pleasure to be here today. Just want to confirm, can everyone see the screen?
Yes, please go ahead.
Okay, great. Well, again, it's a pleasure to be here today, and I thought I'd begin the presentation with just a stage setter here. As the previous speaker mentioned, there really is a global imperative to transition to renewable energy resources. Extreme climate weather-driven events are now pretty much the norm, particularly in Western states in the United States. And deadly weather is costing the US at least $145 billion a year. When you add that to a growing appetite for electricity throughout the world, demand rose by 6% or 1,500 terawatt hours in 2021. You're almost at the perfect storm. So the risks of today's aging energy infrastructure are very readily apparent and more dangerous. They're also presenting an increasing concern for energy and national security. And so that leads into the pressing need for long duration energy storage. As was mentioned, I represent ESS Tech, Inc. We are a manufacturer of long duration energy storage platforms. We were founded in 2011. We grew actually out of a research partnership with the United States Department of Energy and its ARPA-E program. And quite simply, our mission is to bring to market the cleanest, lowest cost, long duration energy storage systems. And we really view ourselves as that catalyst for a sustainable energy future. We design and build today environmentally sustainable and low cost iron flow batteries for long duration commercial and utility scale energy storage applications that require anywhere from 4 to 12 hours of flexible energy capacity at rated power. If we look at the global outlook here for long duration energy storage, McKinsey, through the recently launched Long Duration Energy Storage Council, has estimated that there's a need for 140 terawatts. Think about that, 140 terawatts of long duration energy storage. And that sits in that area between what the dominant technology today, lithium ion, can provide and what we and others that are entering the market can deliver now in the years to come. So I want to talk a little bit about, our simple, but what we believe to be revolutionary technology that's really well positioned to solve the energy storage needs now and in the decades to come. So let's talk a little bit about, the benefits of the iron flow battery. The most obvious being that we can provide longer duration, up to 12 hours at rated power. We have no capacity fade and no power fade. We offer a very low cost or total cost of ownership compared to other technologies. In fact, the incremental cost of increasing duration for our technology is less than $20 per kilowatt hour. Why is that? Because our electrolyte is primarily fueled by food grade iron, salt, and water. These are earth abundant, non-rare earth materials that are not generally subject to some of the supply chain constraints that we see associated with the rare earth minerals required for alternative or other battery technologies. We have some of the same characteristics, though, of a lithium ion battery. We have the same fast response time, less than 1 second. But where we sort of pull away is that we offer much longer cycle life with really no cost or marginal cost per cycle. As part of our partnership with the Department of Energy's ARPA-E program, we did extensive testing, cycle testing, short and long cycles on our battery modules, and then followed that up with a very comprehensive forensic deconstruct. And as a result, we're very comfortable stating that we can deliver well over 20,000 cycles over the 25-year anticipated lifespan of our platforms. Safety is also important, not only to our customers, but also to the environment. We are a non-flammable and non-toxic battery, and we don't present any explosion risk. We operate at very wide ambient temperature range, and we'll talk about that in a couple slides down the road. And we're also bankable, thanks to our partnership with global reinsurer Munich Re. And then finally, sustainability. Again, because the minerals and materials that are required for the build of our batteries are easily sourced, ethically sourced, and recyclable, we're one of the most sustainable batteries on the planet. And that was borne out by a very comprehensive report that was put out by UC Irvine, examining from cradle to gate the global warming impact of various battery technologies. So let's talk a bit about how the technology works. If you're not familiar with an iron flow battery, we are an aqueous battery or a water-based battery. And thanks to that food grade, earth abundant iron, salt, and water for the electrolyte, our batteries are very easy to site. They're extremely safe to operate. And just as an example, in the state of California, where we've been permitted at several sites, the fire marshals really like us. Again, because iron flow chemistry doesn't use rare earth minerals like vanadium and lithium, it produces less environmental harm in material sourcing and production processes. That's part of the reason why it's a more affordable choice. As I mentioned earlier, zero degradation over 20,000 cycles. Why is that? How is that? Our iron flow batteries circulate a liquid electrolyte to charge and discharge electrons via a process called a redox reaction. The word redox is basically a contraction of the words reduction, which represents a gain of electrons, and oxidation, or loss of electrons. And we use that same electrolyte on both the negative and positive sides of the equation, so to speak. And that eliminates cross-contamination and degradation. This is why our chemistry remains stable for an unlimited number of deep cycle charge and discharge cycles. And our patented electrolyte design and control system, paired with our simple yet extremely elegant electrochemistry, allows our customers to operate longer at higher efficiency and deeper discharge levels. Unlike typical batteries that are packaged as fixed cells or modules, our flow battery has significantly more energy storage capacity, which gives the user the flexibility to align both the power and the amount of electricity stored, and basically to tailor that to a project's requirements, both today and for the future. Let's talk about how we can scale and where we stack up on cost. So again, because the marginal cost of adding duration is largely driven by the cost of our electrolyte, which is simply food grade iron, salt, and water, we're providing a much more cost-effective solution. We view this as a challenge. We've challenged and guided the industry to really consider a more strategic way to take a look at energy storage. We like to think that we're helping shift that paradigm from traditional calculations of cost per kilowatt hour to a capital efficiency method. And the measurable result is that our iron flow batteries are more than 15% more capital efficient than lithium ion batteries. Let's take that a bit further. So after testing various configurations of our iron flow battery 24 hours a day, over hundreds of cycles per year, one thing became pretty clear to us. The battery doesn't generate revenue or a return if it's simply sitting there and idle. And with no cycle limitations or capacity degradation with our technology, our customers are really free to exercise it daily or even multiple times a day. So, we work with our customers who represent utilities, both here in the United States and large-scale C&I customers and nameplate developers, to really maximize the benefits and unique characteristics of our iron flow battery technology. So as a further example, a typical lithium ion battery uses or use assumption is to charge it for 4 hours, discharge it for 4 hours, and then let it sit idle 16 hours a day. But the energy transition underway in the United States and around the world really calls for something different. And we believe that the answer is pretty simple. Lithium ion batteries have very limited cycle life and actually degrade or reduce capacity every time you use them. The ESS iron flow battery, however, has neither of these limitations. And with that unlimited cycling as a key feature of our products, our customers really never have to let their storage asset sit idle. So instead of limiting the battery to a single use, we work with our customers to start thinking about longer duration. And our technology really makes that possible. It makes it possible to stack those multiple use cases for more than 4 hours of discharge from a single battery asset. And combining those multiple use cases will not only diminish the future capability of your battery, as sustainable iron flow technology experiences zero degradation with use, we also maintain 100% of our nameplate capacity. So our customers really don't have to augment throughout the 25-year lifespan of our asset. So to put it simply, the harder you exercise the battery, the greater your return on investment is for the asset. We also view bankability as something very, very important. We recognize that as a newer market entrant, though our platforms are commercially available today, bankability can be a concern for customers. So that's why we partnered with global reinsurer Munich Re to launch an industry-first insurance cover for our iron flow battery. This innovative policy means that our long-duration energy storage solutions are now backed by a full 10-year performance guarantee, regardless of the project size, regardless of the project's location. We've also collaborated with Munich Re to develop a separate project cover. What this cover does is ensures a bankable product offering, and that cover directly addresses technology risk, business continuity risk, and can even be extended in order to provide long-term assurance of project performance to system owners, investors, and lenders in the energy sector. So let's talk a little bit about what we're in production for today. What you see here is our energy warehouse system. The energy warehouse is a fully containerized turnkey platform. It's primarily designed for behind-the-meter solutions. Our first commercial deployments were in 2015, and we launched our Generation 2 or Gen 2 platform in 2020. It's easy to permit, it's fast to deploy, again, the same response time, and it provides flexibility to generate multiple revenue streams and certainly help our C&I customers achieve their resiliency objectives. But we're also very much looking to the needs of the utility space. And that's really where our Energy Center platform comes in. The same power modules that we produce that go inside our energy warehouse container are repackaged, if you will, and put on a larger powertrain or skid. The tanks, which provide the duration, are sited external, and that provides infinite flexibility for solutions that can deliver up to 12 hours at rated power. Think of it as a battery in a building. The first of these systems will be deployed later this year and early next in the United States. Let's talk a bit about a competitive comparison for long duration storage. We touched upon most of these areas earlier in the presentation, but again, from a low cost at 4 to 12 hours, we are extremely competitive. We're commercially available. We're not captive to the same supply chain constraints and concerns as other chemistries. We deliver that unlimited cycling capability with zero capacity fade. Our batteries like the heat. They can operate at a very, very wide ambient range. In fact, every time you cycle the battery, you're generating an exothermic reaction. We're environmentally sustainable, and we present no fire, explosion, or toxicity risk. So I'll end here with talking about, the benefits, or to recap the benefits of our technology. 25-year design life without any capacity phase, very cost effective. We are a proven field tested technology that's commercially available today, and we are exceptionally easy to site and deploy in some of the most complicated markets in the United States and certainly around the world. So with that, I'd be happy to take some questions.
Adam, thank you very much for this interesting presentation. We have a lot of questions, but I will try to go through them quickly. And two questions at the same time. What is the CAPEX range for these technologies? Second question is, what is the standard values for minimum and maximum SOE or power operating range or normal discharge level? Over to you.
So let's talk about at scale. In the utility space, let's just take a 50 megawatt, 10-hour configuration. And let's say that it needs to be or reach COD in 2024. Depending on the market, you're looking at anywhere between 206 and roughly $237 per kilowatt hour installed. In terms of maximum range, again, the Energy Center platform is extremely scalable. So we can go from 3 megawatts all the way up to the gigawatt range.
Thank you. What kind of round trip efficiency does the ESS solution have? Second is, could you please show some real data that the ESS system could work at the customer site?
Sure, and that's actually a good opportunity to reference some case studies, and we'll just progress a couple slides there. But on the DC-DC side, the RTE is between 65 or 68 rather, and 70%. But let's talk about some real world case studies here. So we are currently working with a domestic utility for a microgrid that's part of a public safety power shutdown mitigation program in the state of California. It's a solar plus storage microgrid and contains an array of our energy warehouse systems. The benefits are basically multi-day resiliency for critical needs, including a fire station, a healthcare facility, and other critical infrastructure assets. So why are they working with us? Well, one, the safety aspect. The battery is non-flammable, it's non-explosive. Two, because the battery doesn't degrade, during non-wildfire season in the state of California, the utility is going to operate the battery to participate in the CAISO market to accelerate the payback period. If we take a look at another example here, a front of the meter microgrid utility owned. This is in southernmost Chile. Our long duration batteries are going to be supporting a remote grid served again by run-of-the-river hydro and diesel gensets. So why are they working with us? Our long duration batteries will basically displace the diesel gensets for roughly 10 out of 12 months out of the year and provide $3.1 million in incremental savings over lithium ion batteries and over the total project's lifespan, avoid 12 years of diesel genset emissions.
Thank you. How will the EU's desire to rapidly reduce dependency on Russian natural gas accelerate deployment of long duration storage for the electricity sector? Second question, is an
Well, let's address the first one because I think it's an important one, and I probably won't remember the second one if I don't address the first one. Yeah, this is a very real concern, and we're seeing this in real time today with the conflict going on in Ukraine. Ukraine relies, while not as heavily on Russian gas as some of its neighbors, it does rely heavily on coal. All right, and there are certainly models that we're seeing emerge in other European countries, whether it be Germany, Sweden, Finland, Romania, where at the state level, they are very much looking at how to displace that Russian gas with a mix of renewables and long duration energy storage. Is it going to happen overnight? No, but if anything, the conflict between Russia and Ukraine has accelerated thinking and planning on how to displace reliance on Russian gas and replace that with renewables plus long duration energy storage. Next question.
Thank you. I'm going to take one more question, Aaron, and then if you have time, you may answer it online. What is the rate of self-discharge and how much operation and maintenance is expected every year?
Great question. The self-discharge is negligible. So again, unlike that lithium-ion battery in your cell phone, when you power it on, it's not self-discharging at any sort of noticeable or measurable rate, which means you can leave the battery powered up and then use it when you need it. That's not the best use case for a long duration battery like the iron flow battery. But to answer the question, self-discharge is negligible. O&M is infinitely easier for an iron flow battery than, say, alternative chemistries that require things like fire suppression systems, fire rings, spacing requirements. The iron flow battery is much easier to operate and maintain. Again, the anticipated lifespan is 25 years. So let's talk about what will likely need to be serviced during that 25-year lifespan. Really inexpensive components, the power electronics, industrial pumps, pump heads, and motors. What will not need to be replaced are the power modules, which we manufacture via a fully automated, fully epoxied process, thus having eliminated the need for things like O-rings and seals, which earlier flow batteries relied upon. Nor will you need to top up or replace the electrolyte because our systems are completely sealed and closed looped. That coupled with a patented electrolyte health management system that we've developed, which is in essence a proton pump. When you cycle and discharge the battery, you're essentially refreshing or replenishing the electrolyte with each of those cycles, thus maintaining the health of that electrolyte.
Great. A couple of more. In case of the SDG and E project, when will ESS system be online? And what is the cost per kilowatt as compared to lithium-ion battery?
Well, the system will be fully commissioned over the next couple of weeks. All of the systems are at site. So I look forward to sharing the announcement when it goes live.
What is your current international market share?
We're seeing a lot of interest and growth from the Australasia region. We publicly disclosed intentions vis-a-vis the Australian market. We're seeing a lot of growth also from the EU and LATAM.
Excellent. So with this, Adam, I would like to close today's session, but thanks a lot for this interesting presentation. We have some other questions for you. If you have time, please respond to them. But thank you very much. And there's one last announcement we have. The Energy Storage Partnership of the World Bank is doing another webinar on pumped hydro, proven large-scale energy storage. This will be on June 16th at 8 Eastern Standard Time. You may register it on the ATA Insight site like you have registered for today. And this will be another very interesting webinar where we will have speakers Alex Campbell, who is the head of research and policy at IHA, and Rebecca Ellis, who is the energy policy manager at IHA. I look forward to have another productive discussion with you on June 16th. But let me thank again Adam and Aaron for the useful insights. Thank you very much. Good day.